Hey guys, welcome to another CNCM lecture. This one's going to be on states. Huge thanks to Jonathan for putting together the slides. So, what is states? States is a way of solving probability questions which typically involve a person or some sort of object that can literally be in many different states. It can transition from one state to another with a given probability. Generally, these problems will involve some sort of random process that terminates under a certain condition. So it could be a two-player game or an infinite walk. The concept is best illustrated by examples, so let's do one. Problem 1. Monica and Chandler are playing tennis and are currently tied at a deuce. Let the probability that Monica wins a point be m, and the probability that Chandler wins a point be 1 minus m. Find the probability that Monica wins the game. If two players are tied at a deuce, one player must have 2 more points than the other in order to win. So there are 3 different possibilities for who will get the next 2 points. Either Monica can get the next 2 points and win the game, Chandler can get the next 2 points and win the game, or each of them can get 1 point and they're back to a tie. The probability Monica gets the next 2 points is m squared. The probability Chandler gets the next 2 points is 1 minus m squared. And the probability they remain tied is 2 times m times 1 minus m. And the 2 comes from the fact that either Monica can get the first point and Chandler gets the second, or Chandler can get the first point and Monica gets the second. So what we'll do is let the probability that Monica wins be p. If they remain tied after the next 2 points, they come back to the initial state, and the probability Monica wins from there is p again. As a result, we can get the following equation. P equals m squared, where m squared is the probability Monica wins the next 2 points, plus 2 times m times 1 minus m, that's the probability they remain tied after the next 2 points, and you multiply that by p, because there's a probability of p Monica wins from the tie on. And of course, the third possibility is Chandler gets the next 2 points, but in that case, Monica loses, so we don't consider it in the sum. And from this equation, you can solve from p and get that p equals m squared over 2m squared minus 2m plus 1. All right, second example. This one's from an AMC 12. A square is drawn with vertices at 2, 2, minus 2, 2, minus 2, minus 2, 2, minus 2, and a particle starts at 0, 0. Every second, it moves to one of the 8 lattice points closest to its current position. So that could be either horizontal, vertical, or a diagonal move. And since there are 8 possibilities for where it could go, the probability that for each, the probability will go in a certain one of the directions is 1/8. And eventually the particle is going to have to hit the square at either a corner or one of its interior points on the sides. And we want to know what's the probability that it hits a corner. So what we'll do is we'll define a function p that takes each coordinate point and spits out the probability that the particle, if it starts there, will hit one of the corners. We're looking for the probability the particle hits one of the corners starting from the origin, so we're looking for p of 0, 0. So let's get the diagram here. So since the square is symmetric, each of the four corners of the square will have the same capital P value. Each of the interior points on the sides of the smaller square will also have the same probability of hitting the corner. And the probability the particle hits a corner from the origin could be a different value. So, well, there's three different possible p-values on this 2 by 2 square. We'll let the probability at the origin be x, the probability at the corners be z, and the probability from one of the interior points on the sides be y. And then from there, we'll set up a system of equations. So if you start at the origin, there's a half chance of going to an interior point and a half chance of going to a corner. So x equals 1/2 y plus 1/2 z. If you start at a corner, there's an eighth chance that you'll move diagonally to the corner of the bigger square, and that's what we want. So you're going to have to add a 1/8. In two of the possible moves, you'll end up at an interior point. So there's a fourth chance that you'll end up at an interior point. And there's an eighth chance that you'll come back to the origin, so you have to add 1/8 x. And for the remaining four directions, you will not end up at a corner. You'll end up at an interior point of the larger square, which we don't want. So that exhausts all possibilities starting from a corner. And if you start from an interior point, then there's there's an eighth chance that you go back to the origin. These two diagonal moves and bring you back to an interior point, so you have to add 1/4 to y. And moving up or down brings you to a corner, so you have to add 1/4 to z. If you move in any of the other remaining three directions, you'll end up at an interior point of the larger square, which you don't want. And now what you do is you solve these system of three equations, and you get x equals 4 out of 35. All right, on to the last problem. Problem 3. A drunk man stands on the edge of a cliff. If he takes one step to the left, he will plummet to his death. And he has a quarter chance of stepping to the left and a 3/4 chance of stepping to the right. What's the probability he escapes from the cliff? Or really, if you want to think about it as, what's the probability he just doesn't die by stepping over the cliff? So imagine the man's on a number line at the origin. If he steps to -1, he'll die. If he's at a non-negative coordinate, he'll remain alive. So as is usual with these states problems, we let the probability the man dies be p. And note that p is not just the probability that the man goes from 0 to -1 eventually. It's also the probability that if the man were to start at, say, 2 instead, he'd eventually end up at 1, or if he were to start at 3 instead, he would eventually end up at 2. So it's the probability that if he starts at x, he'll eventually get to x minus 1. So what we can do is set up the equation p equals 1/4 plus 3/4 p squared. So this 1/4 stems from the fact that if on the first move he steps to the left, he'll die, and there's a 1/4 chance of that happening. Otherwise, there's a 3/4 chance he steps to the right, and if he does so, then since we know that he's eventually going to die, he'll have to step back to the point 1 left. and there's a probability of p for that happening. And if he eventually steps one left, he'll step one left again to die with a probability of p. So it's p squared because if you step one to the right, there's a probability of p squared you'll end up going 2 steps to the back, or 2 steps back. And you can solve this equation to get p equals 1, or 1/3. And we'll take the answer as 1/3 and leave it to you, the viewer, to disprove p equals 1. And we also encourage you to try to find the general solution for this problem if instead the probability of stepping to the left were maybe 1/2 or maybe 3/4. All right, so thanks for watching. If you enjoyed this lecture, you can check the description for the link to our Discord server where you can meet more passionate math students. Bye.